Hey, what's up, guys? This is Chung here again. So today I'd like to talk about this 854 k-similar strings. It's a hard problem. Okay, so you're given like a strings, two strings, string A and string B, and the string A and string B are k-similar for some non-negative integer k if we can swap the position of two letters in A exactly k times so that the A and B will be the same. And given two strings A and B, return the smallest k for which A and B are k similar, right? So for example, this one, A and B, you only need to swap A one time from swap A and B become B and A. That's why the answer is 1. So here, mm, you need to swap, oops. So you need to swap A and B to become B, A, and C. And then from here, swap the second and third to become B, C, A. That's why the answer is 2. And it asks you to return the smallest k. So what's gonna be the intuition here, right? So every time when you guys see like a smallest, yeah, it asks you to get smallest. So a few things should pop up to your mind. The first one is always the BFS search, because BFS is designed specifically to get the minimum or the shortest value, right? So BFS is the first one, BFS. Second one is the DP or the binary search. Things like binary search. So binary search can also get you the smallest, but probably not for this problem. And third one is the DP, right? DPs can always get you either the smallest or the biggest, right? And the fourth one is what? The fourth one is the backtracking. Okay, so let's check them one by one, right? So for the BFI search, so the BFI search, first thing is the smallest, and the second one is the what? Is a besides the smallest, the second one is we have a starting point and ending point, which is the perfect fit for this problem. We have a starting point which is A, and ending point is B. So the BFS is definitely an option here, right? And how about binary search? So for the binary search, we're searching the answers directly. Let's assuming we have answer here, we have answer K here. With answer K here, we probably still need to try to get with the K here, we will still need to try to do the swaps, the K times basically, or hoping we can get B here. So probably it's not that useful in this case, right? We will not be able to get because we are actually, even though we are giving a K here, we're doing this we're trying basically we're solving the same problem, right? So another characteristic for binary search is that given like given like a fixed k here or a fixed answer here, you so you should be able to convert this problem to a simpler problem to solve, right? But for this problem, even with the same with the k here, we're still solving the same problem, which is not for the BFS search. Sorry, which is for the not for the binary search, right? And third one is DP. So for the DP, mm, for the DP with two given strings here, we most likely will have like a DP I and J, right? So basically, we can try to define something, with the first I's letters and with the first J's letter. Oh, sorry, probably not for this one because we have the A and B I have the same, so the DP is one D. So probably it means that with the first I characters, the minimum swap we can make A and B equal is equal to the value, right? Equals to the minimum value here. And but will this one work? Basically, with the new letter here, let's say with a new letter, assuming the A and B is different, I think for this kind of A and B strings, we always need to check if the AI is equal to the BI, right? So I mean, if you guys remember the added distance from one string to another, we're using this kind of approach, right? But for this one, since the only thing we are allowed to do is swap, so which fundamentally change the definition of the DP here, which means that if we're trying to use a similar DP concept here, we have a equals to B, then of course we can do a DP, right? We can do a DP I minus 1, I equals to the DP I minus 1 because we don't need to swap this. But the problem is else here. If the DP, I'm sorry, if the A and I and the B and I are different, right? And what are we gonna do, right? We cannot swap, right? Basically, because the definition of the DP is that for the first DP I and J here, right, A and B are the same, are equal. But if the A and B is different, if we swap, if we do a swap, we make this AI and BI the same, but after swapping, the previously state will be changed. So that's a violation of our DP, right? So the DP is that all the no matter how we do with the current state, it will not affect the previously state, right? That's one of the characteristic of the DP. So which means the DP is not doable here. Okay. So how about the backtracking, right? Yes. So the answer is yes. So the backtracking we can do it. So I mean actually the backtracking is something like another definition of a DP here. Basically, we have like a backtracking, right? We have like the current, and what we do, we do the answer, right? So the answer is like the minimum of the answer, right? Dot, and then we have a backtracking of what of the new one plus one. Okay, this is more like a top-down DP, right? But this thing will work. But we like similar with the BFI search, we have to come up with like a smarter strategy to choose our different scenarios here. So the backtracking and the BFS will both work for this case. So that's what I'm going to do here. So I'll explain a little bit more for each of the problems while I'm doing the coding here. Okay, cool. So let me try to do the coding here. Okay, first one is the BFS, right? So for the BFS, I'm pretty sure you guys all know the template here, right? So basically we have a starting point, which is the Q, and we have an A here, right? We define the A here, and we have an answer here equal to 0. Okay. And for the BFS search, we always need to have like a scene, right? Scene set. Okay. And at the beginning, we add this A to the set. Okay. And then we'll do I'll define the N here because we'll be using this length later on. So, and the template is like this, while Q, right? And then for this in range length of the Q. Okay, so that's the one of the template. We have a current, right? Q dot pop left, right? And then later on, in the end we do answer plus one, and then in the end we return answer. So this is my way of doing the BFS search. Another common way is that instead of instead of only appending the actual data, we also append the level here, right? The level. Basically, we're appending like instead of a single values, we're appending like a tuple here. So in that case, we can remove this for loop here because we have for each element we already have its answer here. We already have its level here, so that we can just simply remove that, remove this for loop and this pop left here. But I'm still sticking to my own way. So because I'm just kind of used to that. So and right, so if the current is equal to b, right, that's the template. We simply return the answer. Okay. Now is the try all scenarios. Okay, that's the scenarios here. I mean, a brute force way is what? A brute force way is that we try to swap everything. We try to swap all the possible letters in A, which will be what? Which will be O(n) square. Which will be O(n) square, right? So which will be TLE, even though the length is only 20, right? But remember, so for the BFS element, we're looping through everything. We're looping through n squared. That will be too much. So that's why the key the difficulty for this problem is that how for both by the way for both the BFS and the backtracking method, we both need to find like optimization, or we need to pruning our approach instead of trying all the possible scenarios here. So why is that? Because I'll give you an example here. Let's say given like a current A here, do we really need to try all the possible swaps for A? No, right? Because let's say I'll give you some examples here. We have a. Let's say this is A, the current A. So let's say this is the current, and this is B. Okay. So current is AAA. The B is also AAA, and then we have a B, D, and let's see, we have a ABC here, and an FE. Okay. Here we have A, C, A, B, C, A, and D, something like this. Okay. So let's say we have a current of this A and the B is like this. Do we have to try all the possible swaps for this current A here? If you guys, I intentionally write some of the same numbers here. As you guys can see, it doesn't make sense to swap any of the letters here because they are already matched to each other, right? Cool. So that's that, right? Mm, and from here onward, right? So from here onward, I mean, let's say we have okay. So now the B and A. So basically, we start from the beginning and we find the first index. That's the A, the current and the B is different. Now we know, okay, we're basically we need to fix this number, right? So when we fix these numbers, we know what we're looking for, right? We know since B is A and we have B here, we're looking for A, right? So that's why we just from here onward, we're trying to find an A here, okay? But okay, so we find the first A, but should we swap? Should we swap it? No. Why is that? Because the current, this A is already matching with the current B here, right? Basically, if we swap this one, even though we have matched this one, but basically we're breaking another swap, right? So we keep going. We go until we, oh, sorry, I think I'm giving like a bad example here. So, and what I mean here, this is A, this is F. Sorry, yeah. So now this is a no, it's not an option, but so, and this is our option, basically, See, because this A is same as this one, but it's different at this app. So basically, even though we're swapping this one, we are only making this a better options here. So this one is kind of like a greedy approach here. You know, that's basically is helping us to reduce, remove some unnecessary swaps. Okay, and basically that's our optimization approach. And we do and we try out everything of this. Basically, we yeah, and we know we are making one swap because this one swap is all we need, right? We make one swap and then we know, okay, we got a new strings, right? And we increase this answer by one, and we append this new string back to the queue so that this new string can be processed again later on with probably with, and we'll see if that string can give us the answer, right? Cool. So like like I said, we're gonna start from the beginning, right? And then we have a while, actually while we are since we are going to do a swap and the string is immutable in Python, so I'm going to convert this string to a list first, right? So we have current here, and I'll be using this current list starting from here. So while current list I is equal to the bi, right? So that's how I moving forward. Okay, so we have a B, right? A. So now we're at A here. We're at this location, right? So now I just need to try all the J's, right, in range I and N. Okay. So, oh, sorry. So why is that? I think I didn't say this one very clearly because let's say we have A, and then we have a B here, and we have A, right? So let's say later on we have a, you know, C, D. I don't care about this part. Maybe F, E, and A, B, and another A and C. Okay, because the reason I'm doing a for loop here is I'm starting from this location. I'm looping through to the end. I'm going to try to find all the valid candidates here. In this case, it's both these two A's, and I'll be doing the swap for both of these two cases because those two indices are equally the same, equally equally the same in terms of the best option here, right? So that's why I'm going to do a check. But first, like I said, we only do the swap of what? The first one is the bj, right? So the bj is not equal to the current list j. So like I said, if this index has already been the same, has already matched the b here, we don't swap. And what? And the bj is currently equal to the current list of, sorry, the bi, 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 current I. Sorry, it's the current J. Yeah, sorry, it's J, because we're trying to match the ice ladder, the ice ladder with the with this current. So this is I, right? This is I, and we're trying to match the J, the ladder from J with the ladder from B in the I here, right? That's why I'm going to do a BI equals current J, because it means that we have find a valid swap candidates, right? And then we just do a swap. Okay. So I mean, just doing the swap is just like this, right? Current list I and current list J is equal to this, right? So J and I. And every time when I do the backtracking, oh, by the way, since we're doing like a for loop here, every time when we're doing like this swap to a list, we'll revert it back. That's how we do the backtracking, right? Because we don't want to, after this for loop, because for each of the swap, there should be having the same base case, right? That's why I'm reverting the change for the next for loop. Okay. So, and we have a temp A here. I'm going to join that because I'm passing the string, not the list. So I'm doing the current list here. And if the temp A, right? So if temp A is not in the scene, so and here is again the part of the BFS template, right? Append dot temp A, right? And then we do a scene dot add, right? Temp A. Okay. Cool. So I think that's it for the BFS. I think we can run it here. Yep. DQ. QUE. Okay, sorry. All right. Submit. Cool. As you guys can see, so this one is it's pretty fast, right? Basically, because we are we have optimized our approach. We only select those scenarios that can lead us to the final answer. Otherwise, it doesn't make sense to do some bad swap. Okay. Yeah, so I think that's the BFS. So now the backtracking. Okay. So let me try the backtracking. So for the backtracking, I think it's similar as a BFS. And so we just define a backtracking, right? Backtracking, and I'll do a current A here, right? So and then I'll do the return here, the return backtracking of A. So actually this backtracking is more like a DP because because why is that? Because here since we are not passing the index. Okay, we're not passing the index. With the index we might meet. Never mind. Since we're passing these strings here, right? And we could have seen the similar string. That's why we need a memorization for anything that we have seen so far. And the logic for this is like this. So and n equals to the length of A, right? So for the backtracking, right? And actually it's not a backtracking, I will call it a DP here. It's more like a DP. It's not like a backtracking here. But we'll be using the backtracking here, just like how we did in this like BFS search. if the current A is equal to B. Okay, the base case is basically that's return 0, right? Otherwise, the if the current A is in the memorization, right, we return the memorization of the current A, okay, and then we have answer here. Okay, so the answer is, since we're getting the minimum, we are going to define this value as at the maximum first, and then in the end, I'll finish the template here. Answer, return the answer. Okay, so from here onwards, basically, I'm copying everything here. I'm copying everything here up to here. Okay, okay, and okay, and why is that? Actually, this BFS and this like a backtracking, or we call it DP here, it's kind of similar because we have like this one, right? So up to here is exactly the same as the how we get the different scenarios here, get the valid scenario, and once we have a valid scenario, we can okay. I also need this one here, and then I can just simply do answer equals to the minimum of the answer dot what dp, right? dp of the temp A, and then plus one, okay, right? So just like this, right? That's basically that's the backtracking or the DP. The backtracking is right, it's right here, and this part is actually the DP. What this one does is the at each of the state, right? At each of the state here, we are mm, after finding the valid swap here, we do the swap, and then we'll pass this one. We'll pass this one to the DP method here, and then we plus one. And when the base case for this DP is the top-down DP here is when we find a match, we return 0. Okay, and we will be getting the minimum out of everything. Okay. Mm, yeah, and someone may have a question, So the question is like, we only have like this one like base case, right? Which is the current answer is equal to B, and we are like doing the swap over and over again. If we don't have another, if we don't have another like base case, how can we guarantee that this this recursive call will finish eventually, right? Because for some other DP top-down DP problem, we usually have like an index, right? Basically, whenever the index has reached the end of this array, and then we simply return 0. But for this one, since we're doing the swap, there's no such thing. We always passing the entire modified string. So how can we make sure this DP will end eventually? Okay, so but if you guys watch this solution closely here, we are first for each of the current A here, we're trying to find the first like unmatched letter, and here we are matching that first unmatched letter. This case. So what does this mean? It means that it's similar like what we are having. We're having like an index, like index I here, because at this state here, we have first I letters matched. Okay, and And once we pass this one to the temp A here, we have the first I plus 1 letter matched, right? And every time when we call another DP here, basically we're increasing the matched letter by 1. And by the time it reached the last letter, then we're finding an answer here. And if there's no such matching here, what does it mean? It means that for the for loop here will not find any valid swap option. So which means that that string will not have another like basically that string will not go to the next DP here because the for loop here, we have this check here, it will not find any valid option for that string to be swapped. So that's why with this logic here, it's guaranteed that our DP will stop and it will give us an answer. Cool. Yeah, I think that's everything for this problem. Yeah, thank you so much, guys, for you guys to watch this video. I hope you guys learned something. Uh, cool. Stay tuned. See you guys soon. Bye bye.